Okay, so I'm going to go over how to evaluate a claim similar to the one you guys are working on with the pendulum or the mass on the spring. So, but I don't want to go over exactly the same thing because that wouldn't really be appropriate. So I've got another example. So if we were reading a claim about a student heating some water, and so in this diagram here, I've got like some power source, electrical power, and it sends electricity through this wire here. I guess I could change my color. And as the electricity goes through the wire, it's going to go around this coil and transfer its heat to the water. So we're transferring energy from the electrical power into thermal energy, electrical energy to thermal energy. And so the student has these equations here, and so they're going to make a claim using the equations. So this is their fancy math. So we already know that power is energy transfer over time. This is an equation from chemistry that you may have learned. Q equals mc delta T. And so what these things are, Q is the symbol for heat, and heat is measured in joules like what we're familiar with. Then you have the mass of the material that's getting heated, the specific heat capacity of the material. So that's something that just depends on the material. You look it up in a chart. And then the temperature change of the material. So if you have more material, it's going to take more heat to warm it up. If it's got a higher heat capacity, it takes more energy to heat it up. And if you want to get a higher temperature, of course, it's going to take more energy to heat it up. But then the student also knows about electrical power, which is not measured in joules. That's a typo. It's joules per second, or watts, as we know. And so that's equal to the current times the voltage. And those are things that can be measured with those voltmeters that have been sitting on our tables that other students have been using. So those are measurable things. And then so is resistance. And this is just another way of writing it, that voltage squared over resistance is equal to the power. And so they plug these things together here. So if power is V squared over R, and their machine here can read out the power for them, so it measures V, or they can set the voltage or something like that. And then the resistance of this electrical coil, so this coil here is going to have some resistance. And that's, since it's power, it's got to be energy transfer or heat over time. So there's the heat. And since heat is mc delta T right here, and power has got to be the heat over the time, then we got the over delta T there. So the capital T for the temperature here, and a lowercase t for time. And so if they just focus on the measurable things, like Q is like kinetic energy or potential energy. We don't have a tool that measures that. But there are tools or things that can be looked up for all of these quantities in here. So this is the student's claim. They claim that all this stuff. So just like in your case, they claimed that t squared is equal to 2 pi root m over k or something like that. Here they're claiming that v squared over r equals mc delta t over the time interval. And so we need to evaluate this claim. So what can we do to evaluate it? We'll collect some data. Now here there's a bunch of different variables, a bit more than what we had before. But just like you guys had a time limit, you couldn't do it all. So similarly here, we'll try to limit and just do like one experiment at a time. And so I think, just like in any experiment, you should have two variables, independent and dependent. Everything else should stay constant. And looking at the setup here, we've got this little dial. And so that little dial can be changed, so we can change the voltage. So that would definitely be a good variable to have. So we'll make this a variable, well, just V. Okay, so V is a variable, and so what would be easy to measure, we could stick a thermometer in the water and measure the temperature change. So that could be the dependent variable, which would mean we'd have to keep everything else constant. So we'd have the resistance being a constant, the mass of the water being a constant, the heat capacity of the water as a constant, and the temperature, the time that we let it heat up the water would have to be a constant as well. And so that means if we keep looking at the math here, just thinking ahead, if we rewrite this a bit, we could say that we could get the v squared, or we could, the dependent variable will be the change in temperature. So I'm going to put delta t equals. So delta t will be equal to, and then I do my algebra, so multiply the times on both sides, divide the mass and the heat capacity on both sides. And so delta t will be equal to the little delta t over m, c, and r, all those things. And then I'm going to write it kind of separately, v squared. Writing it kind of separately is just going to make it easier for me to identify things. So we've got our constants there, and then we've got our dependent variable and our independent variable. So that means that if I, just thinking ahead again, if I want to evaluate this claim that the student has, then I could just make a graph where, since this looks like y equals mx, I will put my v squared down here and my delta t up here. I could also graph v and delta t just to see what it looks like. Usually people do that. But I know that I can test this claim because since this has a proportional look, as long as I plot v squared, then I'm going to have these three chunks, just like I've got three chunks down there, then I should get a straight line on this graph. Now, of course, on the other graph with just delta t and v, that should look like some other equation that we're familiar with, like y equals kx squared, right? Because my v is squared. So if you plot x, you should end up with some sort of curve, and it would look like a parabola that's going to open up, and it's not shifted from the origin because there's no plus anything, and so it's just going to open up like that. So that's what I'm expecting. So when we get the data, this is what we end up collecting. So I've got my little table down there. I plotted the points. I haven't linearized it yet. When I look at it, it looks pretty linear, which isn't great because that's not what I'm expecting. So if we put a trend line, a straight trend line on there, it fits pretty well straight. I'm going to stick an equation on there for no good. This equation is pretty useless because I don't have a theory that tells me what any of those numbers would be. So this is kind of a worst case scenario to conclude with, because all we can really say is that it's like 0.283, just looking up here at the slope, 0.283 degrees Celsius per volt, which is true, that's what the slope means, but it's not giving us any other insight. And we know it shouldn't even be linear. So if we try the function type that matches our theory, this is called a power relationship. Either of these, so this is a power and this is a power. It's just that in this case it's a power of 1, and here it's a power of 2. But a power of 1 is usually called proportional. And so, but in any case, it's a power that we'd want to test on there. And so if we go back to it here and we change it to a power series, then we can see a bit of a curvature, and it also fits well. So the data quality isn't good enough for us to tell which one is the best fit. They both fit well. But the nice thing here is that the power is 1.82, which is pretty close to what we're expecting. And so this is a pretty good fit, but it doesn't really matter because the whole point of what I've been teaching is that we should, like the next level of doing this is to linearize, so we're going to go ahead and just do the linearized version. We don't really need that. So I'm going to make another column here. I'll stick it in between here with a v squared. Let's see, I'll type it out. And it's going to have units of volts squared. It's not just volts anymore. And so I'll, at this box, type equals, click there, and then do a second power. It fills it in. And then make a graph of these. And we can see that this one also looks pretty straight. So how is it that we linearize something that already looks straight, and then when we've linearized it, it still looks straight. That can happen because of this scenario right here, where you have a range that goes from like here to here. So we're looking at this little bit of data in here. There's not a whole lot of curvature. And so when we go from this to the linearized graph, we go from basically straight to still straight. And so it just means that either our range isn't big enough, right? If we had a bigger range, then we'd see a really big curve. Or the data quality is not that good. There's a lot of, the points are kind of random, and so lots of different functions would fit through there. In our case, it could be both. Maybe we could have had a bigger range of voltages, and maybe we should have done multiple trials and averaged to get them all to line up better with a particular line. So we'll add our line here, though. In this case, it's important for us to add this trend line because we have a theory about what the constant should mean on this trend line. So when we add the label, we add this equation, we know that we shouldn't have, we shouldn't have an intercept, right? So if I take it, I'll just copy this and stick it on the other page. So we shouldn't have an intercept, and we have an intercept, but is it that big of a deal? So 1.1 is our intercept. When we look at the graph, 1.1 is going to be way down here. We can make sure that we can see the origin, so we can see where that would be. And so it's quite small compared to the range up to 15 or 16 degrees. And so it's pretty small, so maybe we could, and also looking at how much the points jump around here, there's a lot of wiggle room on this graph. So let me just get it to, and I can draw on it. So when we look at this, we could have a line that's a little bit steeper and still make a pretty good fit through those points. Like that's not, it doesn't, the points aren't randomly distributed around it, but it's not too far off. Right, so we got some wiggle room on our slope. And within that wiggle room, we got some wiggle room on the slope value, but also on the intercept. And so the intercept, it's like reasonable that it could go through the origin. It's pretty close. But what about that slope? So the slope of 2, so we got 2.35 times 10 to the negative 3 for the slope. We know the slope units have to be degrees Celsius per volt squared. And when we look at our theory, what's supposed to go in front of the, remember this is v squared, we got v squared there, and we got delta t over here. So that matches up with our equation over here. And so we've got our delta t there, and so our slope should be delta t, little t, the temperature change, sorry, the time interval, over m, c, and r. That's the slope. And we have found that the slope is equal to 2.35 times 10 to the negative 3 degrees Celsius per volt squared. So we can see if that makes sense as long as we know the values of those constants. So in the case of the mass on the spring, we had the spring constant as well as the mass that would affect the period, and so it's possible that we could go back to this claim that the student has and choose a bunch of different variables, and like, oh, we could change the resistance and measure the temperature change with a constant voltage and a constant time, whatever. We could have done a bunch of different experiments, evaluated them all. But it's not, we can actually do quite a bit with just a single one, because based on this equation, we can test the whole theory with one single experiment, because our slope should equal delta t over m, c, and r. So it's like we're testing the time interval, the mass, the heat capacity, and the resistance also in a single experiment, although we could have done multiple ones. But if we don't have time, this is a pretty good way of doing it. So if we stick these numbers in that I have written down over here, then we can calculate what the slope should have been. So it should have been 30 seconds over a mass of 0.25 kilograms and a heat capacity of 4,200 joules per kilogram degrees Celsius and a resistance of 10 ohms. And I don't have a calculator. What's that going to be? Something like that. Okay, 2.86 times 10 to the negative 3. The units are a bit of a mess here. I got kilograms on top, kilograms on bottom. They cancel each other out, but nothing else is going to cancel here. And so I'm going to end up with seconds over joules and ohms, the units for resistance. And then these degrees Celsius are actually like a denominator, so they're going to pop up to the very top. So I'm going to have degrees Celsius up here. So I guess it must be true that seconds over joules ohms must be equal to v squared, but that would be something, or 1 over v squared. But that's not something I'm going to worry about here. But that units can be trouble, and people have noticed. But we don't have any millis or micros or kilos here, so everything's probably going to work out. So I'm going to just hope that works. But now we can see that we've got a pretty close agreement here between what the slope should have been based on the constants and what it is. And so what we have here, I would say, is a pretty good agreement and evidence to support the student's claim. Right? The claim is pretty well supported because the relationship between the variables, it looks like our temperature change is proportional to the voltage squared. So check mark. And we could say approximately if we wanted to. Like it's not awesome, but it's pretty good. And we can also say that the slope supports the rest of the variables in the theory. So that's good. So these are the two things that I've been asking you guys to evaluate, is the relationship between the variables, ideally by linearizing, but we could see before we got a pretty good result without linearizing, just by getting the power trend line, but then also evaluating a constant. So if you have any questions about this, if something I said didn't make any sense or you think I made a mistake, let me know.